Hello, hello. No, that's a good way of making everybody stand still. Alright, so we're going to get started. We are still talking about the Unix kernel, and this is still lecture 2A. We haven't gotten, well, these lectures are big. And I was told at the break that we stopped on slide 15, disk architectures. So let me see, what have we covered so far? The kernel mode. Let me go back to the beginning. Okay, we covered the motivation. Well, yeah, we talked a little bit about motivations. Talked about the kernel last time. Talked about the different parts of the operating system in terms of the services that it provides, file structures, disk architectures, I don't know, a bunch of other stuff. Kernel subsystems is what I meant to say. I talked about file systems, processes, input, output, inter-process communication, memory management, everything that the kernel takes care of. Talked about talking to the kernel in terms of system call interfaces and looking at hardware interrupts. So we covered that already. The user mode and the kernel mode and how things are stored and cached. So the kernel will open up something and have a file table, keep track of all the files that are opened. We have different ways of keeping track of processes as well, with a process control block and process table. We have the execution in terms of the execution mode, where we have changes that go back and forth between kernel and user mode. Talked about the system call interface last time as well, and how we have higher level APIs that work on the lower level system call interfaces and what those is all about. Concept of the trap, concept of the system call, concept of I/O, synchronous versus asynchronous processing. Talked about that already in terms of performing calls, and that the kernel can't just stop and do something for the user. And if the CPU is being used, the kernel is going to have higher priority if their job needs to get, if its job needs to get completed before the user. Interrupts and exceptions, looked at those concepts as well. We covered a lot actually. Process execution levels, looked a little bit about interrupt levels and stuff, high and low priorities in terms of interrupts, and the concept of there being an interrupt table where we have numbers that are associated with different activities that occurred. And then I stopped here, I think. And that's a good recap. Okay, good. So disk architecture. Not anything that's associated with the operating system. Disk architecture exists with or without the operating system, and it's the way that the media is physically organized. So the disk is split into slices of pizza, call them sectors. This is going to be a very high-level overview. You could spend an entire week or so talking about disk architectures, and that would actually be a topic for a hardware course, I think, or a computer architecture course, I think, would do that justice. But what we're doing is we're dividing things out into rings and tracks, and we have blocks of data, and the blocks come in different sizes. What can the operating system do? It can work with those blocks. So several variations of this architecture exists. Many disks contain different scattered, several platters, stacks, and things. Big issue, sequentially reading can be much faster and random readings, and the way that we read the disk is important. So you can read what's on the slide, but I'll kind of summarize the concept of how the disk plays with the Unix operating system. We have disk reading schemes that go out and actually operate, because as I was talking about last time, kernel is in charge of all the hardware. It's our interface to the hardware. So the kernel identifies a method for reading the disk. So it's not going to do it sequentially. It's not going to do it randomly. It's going to do a combination of different things. And how the file system is organized might actually determine which blocks are used that are associated with files and how the files are accessed and read. It's going to be a data structure that the kernel is going to know about, that the kernel is going to work with in terms of how the operating system takes care of it. And it needs to read blocks of data. And it needs to read them in order to put them together in terms of the file and the directory abstraction. And hopefully the disk is self-identifiable. Like at the beginning of the disk architecture, the first couple of bytes are identifying the format of the disk. And so that the operating system, all it really needs to do is be compatible. It needs to be compatible with the drivers and being able to actually identify the disk architecture and work with it in terms of its implementation. So that, I'm not going to read the rest of it from the slides because it sounds like a computer architecture beginning course, actually. So, what do you need to know for this class? Yeah, architecture is important. You have to know about it? No. Different disk now. Current flash memory is totally different than we don't have plates. We don't have an arm that moves back and forth. So it doesn't make very much sense to actually study disk architectures unless you're going to get into hardware configuration. Make your own disk. What we do need is a file system. It's called a subsystem, actually. The file subsystem, because it's not the main system, it's the file system, has the support for regular files, directories. Everything in Unix is a file. So essentially, even pointers to files are files themselves, which is kind of interesting. So we have special files that correspond to the peripherals, such as tape drives, terminals. The devices are all files. So we read and write to streams that represent devices, and the disk is one of them. So we have buffered I/O is what they call it. So we bring something from a disk, read it from the disk, put it into memory, store it, or create a link to the memory that's originally being accessed, and then we go through the link. So we have some sort of a pointer or some sort of a directory or file that sort of sticks to it. Process communication mechanisms such as pipes and sockets are also files. So everything's an abstraction of the file system. This concept of an inode exists, and this is the power of Unix and what separates it, because everybody uses files. Not everything in Windows is a file, though. We have different types. It's not everything doesn't reduce down to a file in Windows. The reason why it does in Unix is because it's all streamed I/O. So we can read and write to this concept. And what we're doing is we're reading and writing to the device via the driver, which is giving us the file abstraction. So the inodes contain the permissions, the owners, the groups, the last modified date, and all the information about each one of the files. So if you can imagine the generic concept of a file, the inode is telling us that this is a device driver, or that this is a directory, or that this is a file, or that this is an open file. And it gives us our security as well. So we don't have this concept of everything written to the disk. So let's take it back and compare it to Windows. In Windows, if we wanted an executable file, we have to call it .exe. And in the header of that Windows file, it says, hey, this was created by Microsoft, and this file is read-only, or this file is a binary file, and this file, it's a self-identifying file. If we change the last name of that file to something else, the file won't run, because the file system and the operating system itself is using the file as the holder of all of the information. Well, in Unix, the inodes hold all the information, not the file. So there's a separation between what's physically stored and what's being used. It's all being stored, but it's a slight separation in concept. So we can call the file anything we want, but all of the permissions, all of the information, who owns it, when was it created, that's all stored in the inodes. It's not stored in the file. So the type of the file, whether it's a regular file, directory, or a special file, is it a symbolic link, which we don't actually have, and I'll talk about symbolic links a little later on. The value of the symbolic link, what it's pointing to. Actually, I'll just tell you what a symbolic link is. In Windows, we can copy something, make a copy of it, and we have two separate directories that are both called, like, we can't use the same name, obviously, but there's two separate pieces of information holding separate data. In Linux, we can create what's called a symbolic link that says it's another pointer to the same directory. So we can modify the same contents without making a copy of it, because the file system structure is stored separately than the actual physical storage, so we can map it differently. So we can take one disk, bring it in, and all the users can have a separate abstraction of what's actually on the disk. I mean, they have their own file structure, they have their own directory structure, and we have these things called symbolic links that we can map to create, let's say, our home drive, or create our build drive or something, and refer to it by different names, but it's really all pointing to the same physical blocks on the disk. It's all linked together. So it's kind of like using pointers, but I don't know, students don't like it when I say the word pointer because they all get scared of it, but it is really a pointer, a symbolic link, but it's not, you don't have to create it like a pointer. So we have, if it's a regular file directory, it contains the location of the disk blocks. The inodes will actually contain, if it's a file, it's going to say, well, it's in this block on this disk. We can have many different disks. We can bring in them all together, which is another kind of a different concept. In Windows, we have a C drive, a D drive, an E drive. We load it all up, and we think physically, actually it is physically stored on the FAT table, allocation table, the structure of that disk. And we have my documents on the C drive, and we have all these directories and stuff. We have the same kind of a block structure in terms of the format when we're using it in a Linux or Unix environment, but the directory structure is separate. So it's not, we don't actually, we know the blocks of the storage, but we can change the directory structure, and we can give ourselves a totally different level of abstraction to that. And it doesn't change any of the physical storage, which is interesting. It's more effective, efficient that way. When we move something, we don't really move it. Why move it on the disk? So we can condense the contents of the disk, we can optimize the storage of the disk, and it stays the same. Fewer reads and writes. So, in terms of reading the directory structure. So the inodes, everything that loads up fast, because we're not loading all that data block by block by block from the disk and bringing it all up into memory. Instead, we're just loading up the inodes, and we'll see that when the boot happens. So what do we got here? Direct pointers to blocks 0 through 9, let's say. Indirect pointers to the entire disk. Double indirect pointers. Okay, pointer, 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 pointer. We got the point. It's all pointers to blocks. Those are the inodes, essentially. The layout of the file system. First logical block is the boot block. Kind of, when I talk about file systems, like any file system, in terms of the Linux Unix abstraction, we have different types of file systems. The different types of file systems are sort of like different types of files. It gives us different properties, different characteristics. So we have some file systems that can hold, the files can be bigger than some other file systems. Or the names of the files can be longer. Or they're stored differently. There are different lengths. The reserves or the spaces between the files are different. All sorts of different implementations of file systems throughout the years. And we have the ability to load in any file system that we want that's supported, that we have a driver for. So we load on what's called file system support, and then we can read in a FAT32 or FAT12 or HFS Plus Mac version, or a NTS Plus or something for Windows, in terms of the different types. And those are examples of different types of file systems, as we're probably familiar with other operating systems. So the first block is usually the boot block, starting of the operating system itself on our physical disk. And then the second logical block, the super block, contains information of the free pages, the inode list. So what I'm doing is kind of going through the boot structure in terms of how this stuff is recognized. So it all starts from a disk. We initialize the hardware, we initialize the BIOS goes through and says, hey, we have this, we have this, we have this. Oh, okay, good. And then go to the boot disk. That's the first block segment of one of the hard drives. And you tell the BIOS which drive to select first. Go to this drive, boot from here. Okay. It reads all the information, and well, the first thing it reads is the inode list. So if it's a Unix specified block structure in terms of the file system support, it'll read the inode list. And then the inode list is going to have the list of inodes. Administrators specifically specify the size of the inode list when they're configuring the file system. So you can say, hey, I want to, this is the particular size. Our kernel might reference the inodes by index into smaller inode lists. We can subdivide them out. This is actually kind of unique. The inode list might be different for different breeds of Linux, depending upon different characteristics. Like, we want a system that boots fast. We want a system that doesn't use that very much memory. We're going to have a small, unnested inode list. And then we have the data blocks. Data blocks start at the end of the inode list, and they contain the data and the administrative data and all the things needed to build the file system, essentially. So conversion of the path name to the inode. So here's the interesting thing. You're out in, going back to, this is why I like to do this right after kernel explanation. So you're out there in user mode, you're talking to the kernel, and you want to open up a file. Let's say you want to go to a directory. You do a cd space, I don't know, you do an ls or something. You do some command. The command is interpreted by the kernel. The kernel goes down and performs some activity. So the kernel actually uses the inode list to figure out what's on the disk. So you say, I want this file. Okay, so there's a translation that the kernel does to access the file. You're using the file name because that's the abstraction at the user level. at the kernel level, it's all of the inode names. So we have the name EI. It's just an algorithm that parses the name and turns it into an inode name, essentially. So we have to convert the path name to the inodes and find it in the structure, because we actually have to go through the kernel to actually do any I/O in terms of the file on a disk. So the initial access path to a file is through its path name that we're all familiar with, you know, my documents / resume.doc or whatever we want to call it. And then the kernel translates that into the inodes to access the files, which is how the file system is actually working. So Namei is the algorithm of the path name, one component at a time, converting the path into the inodes based on its name and the directory. So it's kind of like doing translation, and then it traverses through the inode, the tree. Think of it like a tree data structure. It is actually the inodes. And it follows it through the tree and says, oh, okay, here it is. And finds it, resolves it, and delivers the blocks that are associated with the inodes. And voila, here's your abstraction of the file that you asked for. Which is actually kind of pretty cool if you think about it. It's really low level. It's a lot easier to understand than what Windows does. Windows is going to have a totally different way of resolving those names. You type in the name, the runtime environment comes back and says, where is this? And it goes drive to drive. It says, well, it's on C drive. It's on D drive. Okay, and it looks for it the right drive, and then does a searching algorithm and actually finds the physical file that's actually on the disk and loads the physical file from the disk, which is, if you think about it, a lot slower. You want to work with I/O before. Disk reading, slow. Access speed for a disk is very slow compared to other types of memory. So, in fact, memory speed, the farther you get away from the CPU, the slower the memory is. So you want to use the memory that's closest to the CPU in terms of the architecture. So, let's talk about this little algorithm here. So if the path name is absolute, then the search starts from the root inode. And this is just a description of, and this is a really huge, high-level abstract description of what this algorithm actually does. If the path name is relative, then it starts from the inode corresponding to your working directory that's given. And basically the components of the bit are searched and processed left to right through a tree, traversing through a tree. So if you think about the concept, the data structure is optimized in terms of the search. Because what we don't want to do is start at one end of the disk and go to the end of the disk, searching everything on the disk, because it's all on the disk. So hopefully you're getting the impression the inodes take it away from the disk, put it up at a higher level, create a data structure out of it, and you search the data structure, search the tree for what you're looking for, and then it resolves back onto the disk, right? So what happens when you pull the plug on your Linux box? And it's the first operating system to have lost clusters. What's a lost cluster? Well, inode table got messed up. You have stuff in memory that's not on the disk. That's why when you do a proper shutdown, it closes the inode table, closes everything out, puts everything back, resolves any changes that were made while the system was up and running, and then settles everything right at the disk, and we're all done. So next time we boot the system up, we start off where we left off last time. Which is why everyone cringes when you shut down a Linux box. You just pull the power, shut it off. You can do that to a Windows system, no problem. Why? It's all written to the disk already. You're not supposed to have any lost clusters. Windows systems have issues when you open something up and you don't close it from a user mode. You have the file open. Now here on a Linux Unix box kind of environment, you've got a data structure loaded into memory, or using that data structure to access the physical drive. It's not always in sync. It has to actually be written out, and there's a scheduling algorithm that goes out and updates it, syncs it out. So depending upon the timing, you probably lost a lot of files you saved, a lot of changes you did. That's not going to be written to the disk, because we're not, every time we use the disk, we're not reading and writing to it directly. So kind of tells you it's important to shut down a Unix system and not just turn the power off on it. That causes serious damage. And there's a lot of utilities that repair the inodes, repair the disk structure, repair all of everything that's associated with the memory, and then what ends up happening is we have to end up deleting all this unresolved stuff. We have no idea what file this is. We have no idea what file that is. And then just shut it down. And it's not only user mode files. It's kernel level structures that get corrupted as well, because the kernel's got files open as well. So it does cause problems. So the components of the path name resolved. So we have inodes for, we call them working inodes when they're out there And we have decided we're going to traverse the directory structure, go to this area, then we're navigated to a certain area in the inodes by the algorithm, and then we have the working set of inodes that we're manipulating somehow, either reading or writing, or doing something with it. So if the working inode is a directory, the current path name component is looked for in the directory corresponding to the working inode. So if it's not found, we get an error, the directory structure error. So otherwise, we return the inode number. So this is how we get a lot of people who have taken a C course, just a regular old C, and they've opened up files and they've created file pointers. And usually it's an integer value that's returned from the process that creates the open system call, or that runs the open system call that creates the pointer to the file. It's by a number. This is where it comes from actually. It's an inode number that's associated with the file location that you're identifying through this pointer from the user mode. It's actually kind of the same concept of what the kernel does when it goes through the directory structure. It opens up, and everything is a file. So if it's a directory, it's a file. If it's a driver, it's a file. Everything gets opened up in the same path, and same thing, and so we have a number. And so if we keep track of it by a number, we never lose it, essentially. Which is why device drivers always have device numbers in the table. So then we can change the number, we can manipulate the device through the number, through the pointer, so which is how we're doing something. So we have associated with a long path component, we have an inode number that's associated with it. So if the working inode corresponds to a symbolic link, then the path name ends up including the current path component and is replaced by the contents of the symbolic link. For those of you who just came in late, I already explained symbolic links, so I'm not doing it again. So you can read through the video. Alright, so the inode corresponding to the file name, path name, is the component of the inode, the file reference, or to the entire path name. So we have hard drives that are connected to the system, all using the inodes. We have anything that's connected in terms of the directory and the file abstraction, all using inodes. And then all we do is essentially mount things into it, which is why it's called a mount for the file system. So we take an external drive. Most common, you think of this as a USB thumb drive. You connect it to the system. When you do that to a Windows system, what ends up happening is you've got, plug and pray. Plug it in, pray that it finds it. Okay, it found it. And then you got D, E, F, G, H, whatever's the next drive, whatever the next disk level. And it looks just like your hard drive. And you can create a directory on there, you can do all sorts. So then when you pull it out, it's on the disk. Your directory, everything that's on there. And you push it back in, and hopefully you get the same drive letter. Maybe not. It might be called something else. In a Unix environment, there's no plug and pray. But we can actually search for and update and modify drivers. And so what ends up happening is we put it in, and we have to use a command to mount. And what we're doing is we're taking an external device, and we're saying, okay, read this device and put yourself into the file system. And it doesn't get put in, because what we do is we specify a mount point. It doesn't get put in as a drive. It doesn't come in as the abstraction of an external storage device. It comes in as part of the directory structure. In the directory structure, we normally have a MNT, a mount directory, where we have mount disk 1, mount disk 2, mount disk 3. These are entries in the file structure that aren't on the disk. They're in the inodes. They exist in the file system. Once we create it, it gets created in the inodes. When we mount, we bring something else from the outside, and we mount it into the into the file system at that location, mount.disk1, mount.disk1, and we read and write through the inode table, through the directory structure that we specified. So we're not going back and forth to the disk. We sync to the disk when the CPU's decided it has nothing better to do but sync itself, which is not always at the same time in which you're reading and writing. And then it decides, oh, we have idle time, let's update ourselves. So if you pull out that disk without unmounting it, it's the same thing as if you turn the plug off and did not shut properly down the Unix server, you just turn the power off, you're going to have lost files, and you're going to have lost problems. But if you think about it, let's say, for example, we have an iPod, and we have an application that reads everything from the iPod and copies it somewhere or does something. We could take 20 iPods, all connected, and it's all the same iPod according to the operating system. Unix, it doesn't know the difference between that drive and that drive and that drive. They all mounted to the same melting point. It's the same drive, according to the Unix system. And so you can actually kind of generically use drives and disk space. As an example, you have an external disk cabinet full of drives. It's terabits of data that you're using for your web server. One of the drives collapses and dies and decides not to work anymore because it's one of those old ARMs and the ARM's rusted and it can't work anymore, it has arthritis, so the disk stops working. You just pop it out, put a new one in. Same directory structure, same disk, same everything goes on, just as if it was the old drive. So you can possibly imagine we have an extendable system. We can add more memory, we can add more space. If, for example, mount disk 1, the other USB drive that you bought 5 years ago only had 256 megabytes on it. Now you have one that has 4 gigabytes, so put the 4 gigabyte drive in there. Now you got 4 gigs at directory location. You don't have 256, you got 4 gigs now. So you can imagine it's a lot more flexible. You can upgrade the system easily. You have more extendable, more reusable drive spaces and stuff, because you could pull that disk out, mount it to something else somewhere else. Mount it again. Unmount it, mount it into a different area of the path of the directory structure. So it's definitely a lot more flexible than I would say in a Windows environment. So what is this? What is this mounting file system slide says? Well, when Unix is started, the directory hierarchy corresponds to the file system. Usually it's located on a single disk called the root device. This is where we come up with root. Because if you think about the concept, we're booting the system. Even Unix gets booted. We have a master hard drive. We have a main hard drive that has root on it. If we lose root, the whole system goes down, if you think about it. So we do have one drive. That is important, but we can always move root. We can always move the boot location as well of the system. But we load the disk up, we mount it. We have a mount utility. It's actually M-O-U-N-T. You can type in mount. In fact, I can mount USB drives if I want into my directory structure on my MacBook if I wanted to. It allows super users to slice the root directory into a file system and into the existing directory hierarchy. What is a super user? Well, one with admin privileges. Mount is not a utility you're going to give, well, some mount. Actually, root access you're not going to give to all of your users. You're only going to give access to the mount utility that they can use in their own home directory or something, because they might have iPods or USB drives that they're going to want to mount into their system. But essentially what the operating system is doing from a boot perspective is it's mounting the root drive, and that's how the root drive appears, and it actually gets mounted as root, so it's called root. And then everything else gets mounted after root in the hierarchy. So that's why we always see the disk file system hierarchies. You always see that one backslash, and that's root. Some systems actually call it root, sometimes it's just the backslash, or excuse me, it's the forward slash that I'm mimicking my hand signal as a forward slash, and I'm calling it a backslash. So. I'm so used to Windows. There's a backslash in Windows, forward slash in Unix. So it's a starting point, or the smallest area of the tree, the highest point in the tree, and then everything else gets mounted below it. So we have a hierarchy that exists as well. And the file system created on the other devices can be attached to the original directory hierarchy as well, which is an interesting point. Let's say you've got a Unix box and there's extended file system being used, extended 2, let's say, and someone says, "Hey, here's my disk for my Windows XP system. It's a VFAT. No, it's a, I don't know. Let's call it an NTFS system." And then what we do is we mount into our directory structure this NTFS formatted hard drive. And when we mount it in the mount instructions, we say the format is NTFS. Or let's say someone gave us a disk that was formatted for the Mac system. So we can mount it in using an HFS plus. So we say the type of disk that it is, the location that we're going to mount it, and these are all the parameters that are available for mount as a command. So now we can have a directory structure that's using a Windows disk, a Mac disk, a couple of Unix drives, and we don't care what format the disks are actually in, but we've added on and we've loaded file system support and a mount point for each one of these drives. And now we can actually talk and pass files back and forth between all of these different systems if we wanted to, and use them all together, instead of just being stuck with Windows or just being stuck with a Mac or something. Actually, Mac systems will read Windows drives. The only thing that happens is Windows systems don't read Mac drives. But it works the other way around. So Windows is the only operating system out there that's not compatible with anything else, really. It's the main thing that's the most popular, though. So when the mount is established, users are unaware of the cross-mount points. And you don't know where it came from. Actually, you just see it in the directory structure. File system may be detached from the main hierarchy using an unmount utility, as I mentioned before. So we have mount to mount it, unmount to unmount it. Links do not work across mounts in terms of the system V. That's a version of Unix in which did not provide cross-mounted links, where the mount was crossed between multiple drives. It's not going to work in terms of updating information, writing information. So here's an example where we've got a mount to the directory point dev floppy, mounting a floppy drive. The mount point is MNT. It's common actually to use that. You don't have to. You can call it anything you want. Call it my floppy drive. And you read and write to it. It's a directory location. You read and write to it as if it were a disk. So it is a disk actually. So it's referred to as a directory entry point. And then the unmount command just says unmount it. Unmounting closes the drive, syncs it, writes everything properly, so you have the ability to save your information. So the kernel maintains a system-wide data structure called the mount table, and that allows multiple file systems to be accessed via a single directory hierarchy. We only have one directory. In a Windows system, we have every single disk has its own directory. Unix only has one directory for the entire system, which is different when you think. Mount and unmount system calls modify the table in the following way. With the mount, an entry is added. So think the kernel is keeping track of all of these mount points or mount tables. So the device number containing the file system. Going back to what I said about devices and sequential numbers for INODES. That's what it's referring to. Everything is numbered. So device 1, 2, 3. It actually starts with 0. So you usually have hard drive 0, 1, 2, and that would be the device number. A pointer to the root inode of the newly mounted system is established and is made an entry into this table. The pointer to the inode of the mount point. So we have the mount point, the root inode, and the pointer to the file system, that is specific mount data structure for the newly mounted file system. So we have all of these pointers that we keep track of the information in a table, and the kernel knows exactly where everything is. So the unmount does consistency checks, checks the kernel, checks for any open files, closes them, hopefully, and makes sure, flushes out superblocks, flushes out buffers, cleans up the memory, cleans up the inodes, writes the inodes back to the file system, removes the mount entry from the table so we don't think it's open anymore, and removes the mount point mark, and so it cleans it up, makes it smaller so we have fewer mount points to actually work with. So people who have a tendency to put disks in, take disks out because they're so used to Windows. Issues. We don't have plug and pray in Unix, but we have it in Windows. Windows takes care of it for us. Unix isn't going to take care of it for us. So. There's some utilities you can actually install a package for plug and play in Unix for Linux systems, so you can do the same thing. You can put your disk in, take your disk out. So. In fact, if you load that DSL Linux, it has a plug and play module. So you plug it in and you'll see on your desktop, oh look, it says B drive or D drive or something, you know. And it shows up as a drive level. It looks like Windows, actually. So, talk about processes. The entire system is based upon processes right from the boot. In fact, processes are the subsystem that is running the entire system. Every process on the system can be identified in one of 6 states: running, runnable, sleep, suspended, idle, and zombied. We have daemon processes not on here. We have zombied processes. Those are the 2 that you normally are the ones you don't see until you start using Unix. Most people know about running processes. Every time you double-click on something in your Windows directory or your Windows desktop, it opens up and creates a process. In Unix, processes have could have shareable space. Windows, they don't. In Windows, if two processes collide and both start accessing the same piece of memory, you get blue screen of death. you get memory problems. You get frozen screens, and this happens a lot, actually, more common than you would think. Because inter-process communication is one of the hardest things for an operating system to actually manage. In a perfect world, the user would only run one program at a time in a sequence, and you would not have multi-programming going on. But that's not very usable in today's consumer market. We have to have multiple programs running simultaneously doing a bunch of stuff. It's like walking and chewing gum and doing your homework at the same time. You know, we have to be able to do all of it simultaneously. Otherwise, we're not a strong operating system. And because of that, there's the issue in terms of speed and management of these running processes and everything we're going to do. In a Unix system, we have the ability to program processes. So if you take a systems programming class, you create what's called a thread. A thread is another word for a process. It's a thread of execution on the operating system. You can create those in Linux and Unix. You cannot create a thread in Windows unless you buy some sort of or install some sort of a library that creates a Unix virtual machine on a Windows box, and then you can create a thread. But we have no thread control in Windows. So this is kind of a new concept. So kernel, as I mentioned before, starts up, loads the file, loads all the hardware, initiates the system, gives you the user mode. And usually at that point we're at running process 0 or 1. And then everything else is started by the user. And it's running on top. The user runs a program. They run the ls command. First thing that happens is a process gets opened up. And then we have an example of the process state that occurs. So when a process issues an IO command, it suspends or becomes suspendable. And then it becomes runnable, and then it comes back. Becomes suspendable. So what ends up happening is from the start of the process, we have one that is okay, that's ready. We have one that's running. We have that one that could be running if the user was doing something. It could be sleeping, it could be waiting, it could be idle, it could be dead, it could be lost. So we have the composition. And think of a process, if you're not familiar with the concept, as any runnable program on the computer or any executable command, anything. Everything runs in the form of a process. This is actually true for Windows, although we have no control over it. But it's something you can really see in a Unix environment. So the process, it's a figment of the kernel's imagination. It's the user who wants to run a program. First thing the kernel does is go down and say, okay, you want to run a process? Because you gave me a command to run. Okay, so it opens up and it should have a structure called the process control block that keeps track of all the running processes in the system. It's another table. And in the table, it's keeping track of the process number, and it's keeping track of the process memory space, because it goes out and allocates memory out on the system. This is RAM memory. It says, okay, this is how much memory you're going to get allocated. Inside of the memory, it loads up the code that's going to be executable, because it's got to keep track of all of this stuff. So we have a code area, which is the executable text portion of the process. And then we have the data area that's used by the process. So we have static data that's created. So this would be, I said integer I, integer p, I is equal to c is equal to a plus b, or whatever. You know, I had this heavy-duty math calculation going on inside of my process. It goes out and it picks memory and it allocates the memory in what Windows calls the runtime environment. Kernel doesn't have a similar structure. Instead, it's segmented out into a couple of different other abstractions, such as context switching, processes, process control block, memory management, and a bunch of other different types of services that the kernel turns into the runtime environment when it goes about its business. We have the stack area as well of the process. This is the same. Actually, the three code segments are pretty much the same as in a Windows executable as well. User data and then page tables for memory management. And what ends up happening is we have to context switch these processes. So before I go into each one of these separate sections, I want to finish the big picture. So we load this process. We put them into a table. we're still working with one CPU. So now I'm going to explain why we have dual CPU systems for operating systems in terms of the configuration. One CPU can run one command at one time, and the processing of that CPU is always sequential. We don't have multi-processing CPUs. We have single execution CPUs. So we have a kernel that has a bunch of processes the user says they want to run. So we give a little bit of time to the first process, a little bit of time to the second process, a little bit of time to the third process, and we rotate them through a queue, through some sort of a structure. And then the cycle has what's called context switching associated with it, where we give this process and let it run, and then we pull the process back, save its state, say next process, you run. So we have 5 processes running simultaneously. None of them are actually running simultaneously. The kernel, in its context switching, is managing all of the different activities that are going on and using that one CPU. So we put another CPU into the system. Now we can run twice as many processes simultaneously because we have twice as many workers now. Instead of one guy, now we have 2 guys working this. So we can get through the queue faster, so things run faster, which is why multiprocessing with multiple CPUs makes a lot of sense in terms of the growth of personal computing these days. Because in the old days when we were stuck with one CPU, and the kernel has all of these processes because the user thinks all this stuff is running simultaneously, it's got to do a lot of context switching and get all those jobs done fast enough. Or it's got to do priorities and say, well, okay, all you processes can run first, all you processes can run second. CPUs are pretty fast these days, so most users don't really notice too much of it, much of a lag, because it's constantly working. Hopefully. In a perfect operating system environment, that CPU is working constantly, hopefully. If you work it too hard, it might overheat and die, but that's up to the kernel. Alright, so inside of the process, we have information that supports that CPU scheduling. And we have information that supports the information that's being stored by the process. The user data, the code, what the process is actually doing, its context area, its switching information, all of the things that might be associated along with the memory. So the next part of the slides that kind of goes into a lot more detail in terms of all of these different sections. And I'll highlight, I'm not going to read all this stuff to you, but I'll highlight some of the best parts out of this stuff. In terms of the user area of the process, this is the private user area. This is for the housekeeping information. It's used for the kernel for the process management. So, as I mentioned before, the context switching, this part of the program already ran. The kernel's got to save it somewhere. So it saves it in the user area, so the kernel knows that we've already processed lines 1 through 10. Next time we get time on the CPU, we're going to do 11. It already knows where it's going to stop. So it contains the control, the status information, all of the information that's needed by the kernel in terms of that process execution. The contents are only accessible through the process that is executing in the kernel space. You can't get to that from the user mode. It's stuck in the kernel space. And it's only accessible through the user area of the currently running process. Unless the process is actually running, process is not accessible to anybody, not even the kernel. The important fields in the user area include the pointer to the process table slot that's currently executing the process, because we have a process table slot. The file descriptors of all of the open files that that process might own. Any internal I/O parameters, current directory, root structure, current root, process file sizes, reads, effectives, user IDs, anything that might be associated with it. And also how much CPU time the process has recently used. Sometimes how much does it have left, might be, but maybe it's just whatever the kernel needs. And in the process table, as I mentioned before, the kernel has this data structure that contains one entry for every single process that's opened up and running. And so when you shut the computer off, and you have all these open processes, the kernel structures get messed up. Without, when I say shut it off, I mean don't shut it down properly. That's why we have a shutdown command, because the kernel data structures are going to get all messed up, and then when that reloads again, it's trying to come back where it was left off, and then you've got a bunch of open files, you've got a bunch of everything that's going on there. Process table contains fields that must always be accessible to the kernel in order for it to run. Process entry info. So in the process control block, or the table that's storing the information for the block, we have the different states that might be running. And the state is the running, the runnable, the suspended, the zombies. And the process ID and the parent ID. Every process has a parent. So everything that the user runs is associated with something else. And there's an entire tree that's created of all of the processes. We traverse through the tree, we can find the processes, we know who belongs to what user started what. Some of the processes can be run in the foreground, some of them in the background. When we have a process in which we have killed its parent, or something has happened, something has died or terminated, we can only get it from the children, can only access things through the parent. So when we break the chain, we end up losing processes, and that wastes memory. Because the process itself allocates memory, and then when the process is terminated and it's done, it deallocates the memory. So sometimes what makes Unix systems run slow after they've been up for 20 or 30 years or so, 20 or 30 days or so, is that we have processes that are zombied. We have daemon processes. We have all these processes that can't be shut down and that are still running. That shouldn't be running. They should be out of memory, but they're not. It's kind of like how you allocate, but you never deallocate memory. So the kernel can actually create a slow-running system. Same thing happens in Windows, though. Program crashes, but the memory is still being reserved. The computer still thinks the program's running. So you have less memory that's available. The whole thing runs slower. You have more entries in the process control block, and you've got it thinks it's running, so it's allocating CPU time to it. When it's a dead it's not running anymore. So the real or effective user ID, group ID, is also associated with the process and location of its code, location of the memory, any pending signals, any signals that it's generating, various timers that might be associated with it already. So here's the scheduler that I keep talking about. When we build Unix, we build a Unix scheduler. The scheduler is responsible for sharing the CPU time between all of the competing processes. Because, again, only one command at one time can actually be run. So we have to have some scheme to schedule all of these different processes. Maintains multi-level priority queue. So most Unix systems have what's referred to as a multi-level priority queue, following specific algorithms for selecting which processes are going to be run. So usually we have a higher level queue for kernel level processes, and a lower level queue for user mode processes. And we have in-between queues. And we switch back and forth between the queues. So if all of the kernel queues are empty, then we run the user stuff. So scheduling rules might be associated with a priority. May also be with quantum times, preemptive processes, non-preemptive processes, feedback. All sorts of different things might play a role in terms of the scheme or the algorithm that's used. In terms of preemptive algorithms, one of the issues that I talked about last week was actually where we're going to stop something. Usually the kernel is non-preemptive, especially with I/O calls. So we're not going to interrupt, which means the system just sits there and the drive makes noise and things are happening. It's the kernel working. We're not going to interrupt that, but we'll interrupt the user for that. So sometimes we have to wait for certain things to happen in terms of the kernel activity. So during every second, processes in a non-empty queue with a higher priority are being run. So we have a round-robin type of fashion that's kind of fair, that's used in a lot of schedulers. There might be support for real-time processes in terms of things happening simultaneously, communication with other systems, networking processes. So a schedule is based on priority of inheritance rather than time quantum. Time quantum is nothing more than a term that says this is how much time of CPU time this process is going to get. So you can obviously think you could probably come up with a scheme where you give certain higher priority processes more time so that they can get more work done faster. It's kind of like, being able to pick and choose which people you want working on something and then put those people to work and have them finish the job and then start on something else that's a lower priority. And the concept is called context switching. To switch from one process to another, the kernel saves the process program counter, the stack pointer, and any other information that might be associated to it. It saves it in the user data area so it can come back and finish it later. And that's referred to as what's called context switching. And when the process is ready to run, the kernel picks it up and starts running it again. So it switches back and forth. So loading an executable. Everything in Linux, Unix is in the file in terms of the header for the executable. So we don't look at the file name because remember we don't use the same directory structure. We use a different file, INODE type system. The user compiles the source code of a program into an executable file. And so the file consists of a set of headers. Same thing we have in Windows actually. But the headers describe the attributes of the file, whether we have, whether it's a C file, whether it's a Perl file. And we see that in terms of a lot of the scripting languages that we use when we type in headers on the top that are specifically run by the kernel. Say, hey, this is Perl. Okay, send you to the Perl direction. Okay, this is something else. And then we have the program text of the file, and then we have the machine language interpretation or representation in terms of the binary code. And then we have other sections such as symbol table information and all sorts of different things. So the kernel actually reads this and loads it up into the process space. And this is what's determined in terms of the runtime environment for Unix. So the kernel loads the executable file into memory during the exec system call. So people who have done lower level Unix, Linux systems programming, you can run exec to run anything. It'll run ls command for you or copy command. It'll run any Unix command actually. It also is the file that's, the system call that is used to actually start a process. So we can fork a process, exe from a fork, in which, and if you're not familiar, fork starts a new process or a thread, and then run, essentially. And what ends up happening is that we load this into the 3 different regions of the process space, pulled right out of the file. So we take the file, what is the file? It's an abstraction of disk bytes. So we go out to the disk, we pull the bytes, and the bytes are ordered in which I just kind of went through a few minutes ago in terms of the content that's being saved. We read the header, we read the text, we read the information about it. The text corresponds to the text sections of the executable file, the data to the data executable, to the executable file part. And then we have a stack that automatically created by the size. So we take all the data instructions, we load them into what's called a runtime stack. Same thing actually happens in Windows. But the way that we recall these sections is different because we're running them through a disk read. We actually go out to the disk and read the stuff instead of getting it from the file system. So, when loading an executable, the compiler generates an address for the virtual address space, given some sort of an address range. The memory management unit translates that virtual address into the compiler to the physical memory address, and then voila, we've loaded the executable into memory by giving it address spaces that we correspond with the process, and then we have the process control that essentially the table that the kernel recognizes which process is at which address. This is how the boot sequence actually works as well, which is kind of interesting because the boot sequence in Windows doesn't work the same way people double click on files and run programs. There's a whole different scheme used for that. But Unix is actually kind of simple. It's the same thing that we do to run programs. That's what the boot system actually does. There's a set of files that get opened up and loaded up into memory, and those files, one file goes to another file, goes to another file. It creates a bunch of processes until we're finally done, and then the last process that's created is the shell. Because now we can let the user log in now, and we're done. So all it's doing is loading a bunch of stuff into memory. So the boot and the init process are what people normally talk about. Administrators initialize the system through what's called a bootstrap sequence, which is the same kind of a bootstrap that you may have been familiar with before. It's a sequence of events, of reads, essentially, that occur and loads. So you read and you load into memory. Read and load into memory is pretty much what I just went through in terms of how an executable runs. The program contained in the boot block loads the kernel file system, example Unix, or it could just be an example the root, which is a forward/. After the kernel loads into memory, the boot program transfers control and starting address to the kernel. So it starts running. When it's running, it's just ready. It just goes into a running state. So after initialization, kernel mounts the root file system and handcrafts the environment for process 0. And then process 0 forks from within the kernel, and then process 1 starts, and then process 2 starts, and process 3, and so forth. And we can add stuff. We can say, hey, load this one too, load that one too. And it's really what's referred to as a boot sequence. So it depends on what disks do I want mounted, what do I want to automate. So Linux administrators, Unix administrators, are just creating the boot sequence. Sometimes what we have is called a boot menu. It shows that like grub or something, and it picks what disk you want to start instead. So the boot system loads the menu first, and then the user selects, I want this drive, that drive, that drive, or I want this operating system, or that kernel, and then it goes to the disk. And it just follows a bunch of commands, a script actually. In fact, there's a bunch of startup scripts that you can write as a system administrator to configure the boot sequence. So it's actually not difficult at all. It's pretty much what you do as a Linux user. It's the same thing that you're doing in terms of the administration. The same thing the kernel is actually doing. So process runs, one starts, it creates the user level context for allocating data, reserving memory. Process 1 copies code from the kernel space to the new regions, and then we have the new context for process 1. Process 1 also saves any user registers. Context returns back to kernel mode, and it may also run any types of startup scripts that might be in the exec or the init. So some systems have an etc. INIT program that runs. Some of them have an RC program that runs. Some of them have, they call it different things. But what it is user-level runtime scripts that run at the boot, essentially. So next time, and I kind of went through this kind of quickly, but I see a lot of people have come and gone throughout this lecture. It hasn't really been that long, seriously. But some people just showed up, probably thought the class started at 6. It starts at 5. So, but they may have just registered for it, so not to just in case someone showed up at 6 thinking that the class started at 6, it actually starts at 5. So anyway, I talked fast and I went through the entire lecture, and I've run out of time. Well, I haven't run out of time, but I've run out of material for today. So it means we get to go home early, because I went through the entire boot process a lot faster than I thought I would. So what happens next time? We're going to have more boot and more init information for you, more boot sequence stuff, and customizing the kernel. That's actually the topic for next week. So we're not done with the kernel yet. We're still working on kernel stuff, because 99.9% of all Unix related stuff is kernel stuff. So. Any questions about the boot process, or about mounting disks, or about what the kernel does and what the user mode does? I believe that is the last slide. It is the last slide. So, well, that's actually not too bad. Last time we stayed longer, so this time we're now a little earlier. So, unless we have any questions, we are done for today. So this person just walked in. We start the class at 5 now.
I'm for the next class.
Oh, you're for the next one. Okay. Good. Which one is that? That's the one we just ended. You are here, and this is the next class. We started it at 5 instead of 6. Yeah, that's the problem. I've seen a lot of people just came in like 5 minutes ago. We started it an hour ago. But you don't know that because you just registered for it or something. I don't know. Yeah. I'm just letting you know. Next week, come at 5. And we're actually ending early today. Normally, I go till about 6:30, but you can enjoy the rest of your day. How's that? All right. See you next time.